Good morning, students. Today we are going to discuss a relation. To know about this chapter, relation, the prerequisite is you must have good understanding about sets. In case you do not have my previous lecture on sets, please do contact me and I will send you the same. Let us consider two non-empty sets S and T. S and T are two non-empty sets. A relation between these two sets S and T is a rule which associates some or all elements of S with elements of T. So, what does it mean? It means that suppose S has some elements, suppose its elements are S1, S2, S3, S4, S5, and suppose T has the elements T1, T2, T3. So the set S has 5 elements S1, S2, S3, S4, S5, and the set T has 3 elements T1, T2, T3. Now the relation between S and T is a rule. The rule could be something what we can define, okay, which associates some or all elements of S with elements of T. For example, we can associate S1 with T2, S2 with T3, S3 to none, S4 with T2, and suppose S5 with T1. Then this is a relation by which we can define some or all elements of S is associated to elements of T. Now, what is the fundamental definition of relation? The definition of relation is like this. Suppose S and T are two non-empty sets. A relation between these two sets S and T is a set which is a subset of the Cartesian product S cross T. Right. So, if we define the relation between S and T as a row, okay, a row is the relation is a relation between S and T, then we must have a row is an improper subset of S cross T. Correct? So let's take the example here. So what we can see that we saw that S1 is related with T2. Okay. So S1 is related with T2. S2 is related to T3, S2 is related to T3, S3 is not related to any elements in T. That is fine because the definition says some or all elements of S should be associated with elements of T. So that's fine. S4 is associated with T2, S4 with T2 and S5 with T1. So, if rho is a relation which associates this type of association, then we can say rho is like this. So which is nothing but a subset of S cross T. Right? Okay. Let's take a very practical example. Let us consider two sets S and T like this. Let us consider the set S is 2, 3, 4 and 5, and T is the set 11, 12, 13 and 14. Now, let us define the relation between S and T as S is a divisor of T, or very precisely to say, the element of S is a divisor of the elements of 2. Okay, if we define the relation like that, suppose rho is the relation, okay, so rho is a relation, so it is defined like this. It should contain A comma B, where the first element A belongs to the set S and the second element B belongs to the set T, right? And A is a divisor of B. Now these two we can club together. These two we can plug together and we can write A comma B belongs to T. So what you can do, we can club together these two and we can write A comma B belongs to S cross T and A is a divisor of B. Alright, now how we can construct that relationship rho? So we see how we can construct rho equal to 2 is not a divisor of 11, so 2 comma 11 should not be belongs to rho. 2 is a divisor of 12, so we can write 2 comma 12. 2 comma 13 is not, because 2 is not a divisor of 13. So 2 comma 14, yes, 2 is a divisor of 14. That's why 2 comma 14 should be belongs to this relation set rho. 3 comma 11 not. 3 comma 12, yes. You can write 3 comma 12. 3 comma 13 no. 3 comma 14 no. 4 comma 11 no. 4 comma 12, yes. 4 comma 13 no. 5 comma 13 no. 4 comma 13 no. 4 comma 14 no. 5 comma 5 11 is no. 5 12 is no. 5 13 is no. 5 14 is no. So this is the set. Obviously, rho is a subset of S cross T, because S cross T will contain how many elements? 4 into 4, 16 elements. Whereas rho contains 4 elements. And all these 4 elements are part of the element, part of the set, are elements of the set, very precisely to say S cross T. Okay, so we understood the relation by means of an example. Now we are going to discuss about a special type of relation that is called binary relation. Okay. binary relation is applied to a single set S. Earlier we saw in the definition of relation we need two sets like S and T as we said. Now in case of binary relation we need only one set. So a binary relation on a set S is a subset of the Cartesian product S cross S. Alright? So it is a binary relation what is that? In binary relation what is what we can say is that if rho is a binary relation on S, so rho must be a subset of S cross S, and that binary relation is sometimes also known as, in that way, in the other way you can see it in future, that rho is a relation on S. The moment it is defined on a single set, you can assume this is a binary relation. Okay, good. Now we are going to discuss a very important part of relation is called the several properties of the relation. We will see what is a reflexive relation, what is a symmetric relation, what is transitive relation, and finally what is an equivalence relation. Also we will see something called anti-symmetric relation. Alright, let's see. Before going to discuss this thing, I would like to say you one more thing. Suppose A and B all belongs to rho, then we can say like that implies A rho B. Okay. So this is implied and implies and implied by. That means these are the the way we to express if A comma B, that ordered pair belongs to rho, that means A rho B holds true. Right? And the other way, if A rho B holds true, then A comma B belongs to rho. This is only the way to actually show it. Okay. Now we are going to discuss about that reflexive relation, symmetric relation, and transitive relation. What is reflexive relation? Okay. So before that, you can write here that let S be a non-empty set and a relation rho is defined on S. Now the relation rho is said to be a reflexive relation if IFF, if means if and only if A rho A holds true. So for all A belongs to the set S. That means, that is nothing but, as I said earlier, A comma A belongs to row for all A belongs to S. Then it is known as reflexive relation. Next one is called symmetric relation. Okay? If A comma B belongs to row implies B comma A belongs to row for some A comma B belongs to S. We need to understand this in a little bit. For some AB belongs to S. That means in the set S on which the relation row is defined, let us take some elements, two elements AB. Now AB are arbitrary, means for some elements AB, if we see that A comma B holds true, that means A comma B belongs to row. If this is true, A comma B belongs to row, then with this understanding, if we can prove that B comma A belongs to row, then we can say that relation is a symmetric relation. If A comma B doesn't belongs to row, that means A and B are not related by the relation row, then you need to prove that B comma A belongs to row. So that is very important. If we assume that A comma B belongs to row, or if not assume actually in very literally, if A comma B belongs to row, because row is defined to you, you know whether A comma B belongs to row or not. If it is, then you need to prove that then B comma A should be belongs to row. Then only we can say that row is a symmetric relation. Alright. The next one is transitive relation. If A comma B belongs to row and B comma C belongs to row, that should imply that A comma C belongs to row for some A comma B comma C belongs to S. Here we are assuming, here also, if and only if, okay, we can write, okay, so that we are assuming that A comma B belongs to row and B comma C belongs to row. Now if these two hold true, then we need to prove that A comma C belongs to row. And if we can prove that really, then we can say the relation row is a transitive relation. Otherwise not. Okay? Now, finally we want to see if a relation satisfies all these three, that is, if it is reflexive, if it is symmetric, and if it is transitive, then we can say the relation is an equivalence relation. So, what is the prerequisite to have a relation equivalence relation? equivalence relation means that relation has to be reflexive, has to be symmetric, and has to be transitive. All these three has to be satisfied. If any one of these three is not satisfied, then we cannot say that relation is an equivalence relation. Okay? Let us understand by means of example. Okay? Alright. So before that, what I will suggest, please have a detailed look into that reflexive relation. So this is the part of reflexive relation. This is the part of symmetric relation. And this is transitive relation. Okay? I will suggest you spend couple of minutes understanding this very clearly. After that we will go for example. Thank you. Alright. Now let us understand by means of an example. The first example is that let us take the set N, which is the set of all natural numbers, and a relation rho defined on N like that the two elements x comma y belongs to rho if and only if x minus y is divisible by 5. Right? So what is that? I have a set N, is the set of all natural numbers. Okay? N is the set of all natural numbers and rho is a relation defined on it, and rho is a relation defined on N such that A rho B if and only if A minus B is divisible by 5. Correct? Now let's see whether this relation is an equivalence relation or not. First one is that for any elements A, for all A belongs to N, we see A minus A, which is 0, is divisible by 5. 0 is divisible by 5, is divisible by 5. So what does it imply? This implies A rho A holds true for all A belongs to N. So this implies rho is reflexive. That we have proven. Let us take two elements, A and B, belongs to the set N such that A minus B is divisible by 5. If A minus B is divisible by 5, then its negation minus of A minus B is also divisible by 5, which means B minus A is divisible by 5, which implies B comma A also belongs to the set rho. So we started with A comma B belongs to rho, and by means of some subsequent steps we proved that B comma A belongs to rho. So which means rho is symmetric as well. Let's see here. Okay. Here is the right. Let for some A comma B belongs to N, A rho B holds true. What does it imply? This implies A minus B is divisible by 5. That implies minus of A minus B is divisible by 5. Obviously, it is quite obvious. If a number is divisible by 5, its negation is also divisible by 5. This implies B minus A is divisible by 5. This implies B rho A holds true. We started with the assumption that A rho B holds true, and by means of the subsequent steps we are able to prove that B rho is also holds true. That means according to the definition of symmetric relation, rho is symmetric. This implies rho is symmetric. Fine. Now let's see whether rho is transitive or not. Okay. So let's write it here. Let for some A comma B comma C belongs to A and A rho B and B rho C hold true. What does it mean? That means A minus B is divisible by 5 and B minus C is also divisible by 5. That implies A minus B and B minus C both are divisible by 5. This implies if two numbers A minus B and B minus C are divisible by 5, so their addition is also divisible by 5. That means A minus B plus B minus C is also divisible by 5. Okay, so that implies A minus B plus B minus C is divisible by 5. That implies A minus C is divisible by 5.